Now in this lecture I will answer two questions. In the first question we find out the area of this pentagon ABCDE, and in the second question we find out the area of this green shape. So I start with the first question. In the problem we have pentagon ABCDE. So what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interior angles. This is pentagon ABCDE. Consider it has 5 sides, 1, 2, 3, 4, 5, and 5 interior angles. Okay. So in the drawing we have pentagon ABCDE. We know that side ED equals to side CD, side ED equals to side CB equals to side EA equals to 1, side AB equals to 1 minus X units in this left. This is side DC is equals to X units in this left. In addition, we know that this is again EDC, this is right angle, and this is angle EAB, this is also right angle. Again, our task is to find out the area of this pentagon ABCD. So, first of all, we join points E and C together by straight line. And we join points E and B together by straight line. And we extend side BA by straight line in such a way that the extended part will be equal to X units in its length we extended side BA by a straight line in such a way that this is the extended part that it is equal to X units in its length according to our construction. We define this point as point M. And again, line segment AM equals to X units in its length according to our construction. In the next step, we join points E and M together by a straight line. We extended the straight line BA by straight line. In this way, we created line segment BM. When we extend a straight line by straight line, the result is a straight line. Therefore, BM is a straight line. So if we focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle that is the right angle, plus this missing angle, and total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its sides. According to rule 3, of course. So actually, in the next step, we prove that those two right angles can go into each other according to angle side angle rule. So I copy those two right angles in a new page and we prove that they can go into each other according to angle side angle rule. So really, those are the two right angles we come to the original drawing. Note that side MA equals to X, EA equals to 1. So why those two right angles can go into each other? First of all, side MA in this right angle EMA equals to side CD equals to X in the right angle EDC. So MA, side MA in the right angle EAM equals to side CD in this right angle EDC. They're both equal to X and therefore they're equal to each other. In addition, those two angles are both right angles and therefore they're equal to each other. So angle EAM in the right angle EAM equals to angle EDC in this right angle EDC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, side EA in the right angle AEM is equal to side ED in this right angle EDC. They are both equal to 1 and therefore they are equal to each other. So if you found out that those two sides and the angle that is included between those two sides, that is the right angle, in this right angle AEM are correspondingly equal to those two sides and the angle that is included between those two sides in this right angle ECD. And therefore those two right angles can relate to each other according to side angle side rule. So now, if you found out that the right angle AEM congruent, this is the sign of congruent to the right angle ECD according to angle similarity rule. According to side angle side rule. We have two sides and the angle that is included between those two sides in this right angle EAM corresponding equal to those two sides and the angle that is included between those two sides, that is the right angle in the right angle ECD. And therefore those two right angles can relate to each other according to side angle side rule. And because of the fact that they can go to each other, they must have also the same areas. That's to say, they have this line AEM is equal to the area of this line ECD. So until now, we should find out that the area of this right line AEM is equal to the area of this right line ECD. And the two triangles that can go to each other, they must have also the same areas. So, actually found out that the area of this triangle AEM is equal to the area of this triangle EDC. So this is the right triangle AEM, and its area is equal to this right triangle ECD. So if we define the size of this area on this other ECD as Z, That is to say, the area of this triangle EDC equals to Z square root in its length. Then the area of this main right triangle AEM must be also equal to Z square root in its size, because they can go into each other. So, the area of triangle AEM equals to the area of the right triangle ECD, equal to Z, according to our definition. And further the fact that those two right triangles can go into each other, we will derive that EM equals to EC. EM equals to EC. Side EM on this right triangle AEM is equals to side CE, this right triangle ECD, according to the rule that corresponding sides in congruent triangles are equal to each other. This is to say, those two right hand triangles can go into each other, and therefore the two corresponding sides, that is to say EM and EC, must be also equal to each other in their lengths. So in the next step, we prove that the big right triangle EMB can go to this right triangle BEC. But for that, we'll find out the length of side MB. What is the length of side MB? From the drawing, it is very easy to see that MB in total equals to MA plus AB. So the norm MB equals to MA plus AB. So MB equals to MA is X, plus AB is 1 minus X. So MB total equals to X plus 1 minus X. X minus X is 0, so we left only with 1. In total, we found out that MB equals to 1 unit in its length. This is side MB. This equals to 1 unit in its length. So in the next step, we prove that triangle MEB can go into this triangle BEC. So we copy those two triangles in the new page, we prove that they can go into each other according to side rule. Side AB of this triangle AEB equals to 1 unit in its length. Here, this is side ME, this equals to side EC. And EB is actually a common side that belongs to both triangles. Okay, those are the two triangles. This is triangle AEMB, this is triangle EBC that are from the original drawing. So why those two triangles can go into each other? First of all, EB equals to EC. We also know that EM equals to EC. So you know, side EM equals to side EC. In addition, side MB on this side EMB is equal to side BC on this side BEC. They are both equal to 1 and therefore they are equal to each other. And finally, side EB is a common side that belongs to both triangles. You can see that side EB belongs to both triangles. It belongs to triangle EMB, it also belongs to triangle BEC. So you can write down that EB equals to itself. It's a common side that belongs to both triangles. So if you know that all the three sides of this triangle BEC are corresponding equal to all the three sides of this triangle MEB, and therefore those two triangles can go into each other according to side also. And for now, if you found out that this side EMB congruent, this is the sign of congruent to the right triangle EBC and to this triangle EBC, it is not a right triangle. According to angle similarity rule. And from the fact that those two triangles can go into each other, we derive that they have also the same areas. So there are this triangle MEB. Equal to there are this triangle BEC. Together from all that from the fact that triangle MEB can go to triangle BEC, they have also the same area. So there are triangle MEB equals to there are triangle BEC. So what is there are this triangle MEB? There are triangle MEB. There are triangle MEB equal to the base MB times the height AE over 2. Again, it is equal to the base MB times the height AE over 2. So MB equals to the base MB times the height AE over 2. MB is 1 times AE is also 1 divided by 2. So therefore MEB equals to 1 times 1 over 2, that is 1 half. Therefore MEB is equal to 1 half. So there, this side MEB equals to 1 half. So it's in its size. We only found out that area triangle MEB equals to area triangle BEC, and it equals to 1R. With the equation you get that area triangle BEC also equals to 1R. This is triangle BEC, the area of this triangle BEC equals to 1R. So the area of triangle MEB plus the area of triangle EBC in total will be equal to 1R plus 1R, that is 1. So if you don't know that the area of triangle MEB plus the area of triangle BEC total is equals to 1R plus 1R, that is 1. So if you know that the area of triangle EBC plus the area of triangle EMB equals to 1. But what is the sum of those two areas? Actually, quadrilateral EMBC consists of those two triangles, and therefore this triangle quadrilateral EMBC will be equal to the areas of those two triangles that it consists of. That is to say, the triangle EMBC will be equal to 1R plus 1R, that is 1. So the area of this big quadrilateral EMBC will be equal to 1. Repeat again, the big quadrilateral MEBC, this is the big quadrilateral MEBC, it consists of those two triangles, and therefore the area of quadrilateral EMBC will be equal to the sum of the areas of those two triangles that it consists of. That is to say, it will be equal to 1R plus 1R, that is 1. So the area of the big quadrilateral MEBC equals to 1. But quadrilateral MEBC consists of this green triangle EMA plus this quadrilateral EABC. Therefore, the sum of the areas of those two shapes, that is to say, the area of this green triangle EMA plus the area of this quadrilateral ECBA will be equal to the area of quadrilateral EMBC, that equals to 1. So write it down. The area of this green triangle EAM plus the area of this quadrilateral EABC total will be equal to the area of the big quadrilateral EMBC, equals to 1. So again, if you know that the area of the green triangle EAM plus the area of quadrilateral EABC in total is equal to 1. That's the area of this green triangle EMA is equals to Z. So we substitute the area of EAM by Z. So Z plus the area of this quadrilateral B E of this quadrilateral EABC total is equal to 1. Z plus the area of quadrilateral EABC equals to 1. Our task is to find out the area of this pentagon ABCDE. So what is the area of pentagon ABCDE? The area of the big pentagon ABCD will be equal to the sum of the areas of the two shapes that it consists of. The big quadrilateral ABCD equals to consists of two shapes. It consists of this right triangle EDC plus this quadrilateral EABC. Therefore, the area of the big pentagon ABCD will be equal to the area of the great right triangle EDC plus the area of this quadrilateral EABC. So if you know that the area pentagon ABCDE total is equal to the area of this right green triangle EDA plus the area of this quadrilateral EABC. Repeat again, the area of pentagon ABCD equals to the area of the green right triangle EDA plus the area of quadrilateral EABC. According to our definition, the area of this green right triangle EDC is equal to Z. So substitute the area of triangle EDC by Z plus the area of quadrilateral EABC. And again, to do, I should know that the area of pentagon ABCDE is equal to Z plus the area of quadrilateral EABC. But we already found out that Z plus the area of quadrilateral EABC equals to 1. So you can write down here that Z plus the area of quadrilateral EABC equals to 1 according to what we have already found out. And from this equation, the area of pentagon ABCD equals to the area of triangle EDA plus the area of quadrilateral EBC equals to Z plus the area of quadrilateral EABC equals to 1. We derive that the area of pentagon ABCD equals to 1 square in size. Again, I should know that the area that we are looking for in this question, that is the area of this pentagon ABCD E is equal to 1 square in its size. So we finish with the first question. In the next step, I present you the second question, and so the second question of this lecture. In the second question, our task was to find out the area of this green shape. The green shape, it is actually triangle A and B. So we have to find out the area of this triangle A and B. In the drawing, you have a circle We know that side AP equals to 9 units in its length. This is side BQ, this equals to 4 units in its length. This is again APM, that is right angle. This is again BQM, that is also right angle. And we also know that AB is the diameter of this circle. Again, our task is to find out that this relationship that is actually triangle A and B. We have to find out the area of triangle A and B. So first of all, we define the center of this circle. This point is point O. Here we can implement all 7. According to all 7, if a peripheral angle subsides on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle, and this is peripheral angle ACB that subtend on chord AB, that is the diameter of the circle. And according to this rule 7, because of the fact that peripheral angle ACB subtend on the diameter of this circle, it must be equal to 90 degrees in its size. You can see that peripheral angle ACB indeed equals to 90 degrees in its size. So we can actually implement all 7 in our drawing. In our drawing, this is peripheral angle A and B. Peripheral angle A and B subtend on AB, that is the diameter of the circle according to what is given as the question. AB is the diameter of the circle according to what is given as the question. AB is the diameter of this circle. Fill again. Peripheral angle A and B subset on chord AB, that is the diameter of this circle. And therefore, according to all 7, peripheral angle A and B must be equal to 90 degrees in its size. According to all 7, of course. In the next step, we define this angle as alpha. So, in the right line A and P, this angle equals to alpha, this angle equals to 90 degrees, and therefore this further angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. That is to say, 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. According to what is given as the question, PQ is a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line, the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have on the upper side of the straight line PQ at point M? We have this angle that is 90 degrees minus alpha, plus this angle that is 90 degrees, plus this missing angle. In total, it must be equal to 180 degrees according to all 3. So we can write it down. 90 degrees minus alpha plus 90 degrees plus this is the missing angle B and Q. So in total, the sum of those 3 angles must be equal to 180 degrees according to all 3. this side of the equation we have 90 degrees plus 90 degrees, which is 180 degrees, minus alpha, plus the missing angle BMQ. In total must be equal to 180 degrees according to rule 3. We have 180 degrees on both sides of this equation, so 180 degrees will get cancelled, and you left only with minus alpha plus the missing angle BMQ. In total it is equal to 0. Here we add alpha to this equation, and we get that the missing angle BMQ equals to alpha degrees in its size. Okay, this is the missing angle BMQ equals to alpha degrees in its size. So in this right small triangle BMQ, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. According to the rule, the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that those two right triangles are similar to each other according to angle similarity. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, both those two angles are equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you prove that all the three angles in this right triangle APM are corresponding equal to all those three angles in this right triangle BMQ, therefore those two right triangles are similar to each other according to angle similarity rule. So if you know, if you know that the big right triangle AMT is similar, this is the sum of similar to the small right triangle BMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of this big right triangle APM over side MQ of this small right triangle BMQ is equal to side PM of this right triangle APM over side BQ of this small right triangle BMQ. So again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM is equal, over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of the small right triangle BMQ. AP is the missing side, so AP actually equals to 9, so size of AP by 9 over MQ. MQ is the missing side, so this it is, and it is equal to side PM PM is the missing side of electricities. Our side VQ. VQ is 4, so we solve the VQ by 4. So total we found out that 9 over NQ equals to PM over 4. Here we first multiply this equation, and finally get that 9 times 4, that is 36, equals to MQ times PM. So we found out that MQ times PM equals to 36. OA is the radius of this circle. So we define the radius of this circle as well. So OA equals to R. O is the center of the circle. OA equals to R. Likewise, OB is also the radius of the circle that equals to R. In the next step, we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle, that is equal to R. M equals to R. So here we can implement rule 1. We have the radius OM that equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction. That is to say, from this point O, that is the center of this circle, we will do perpendicular on AP. Again, from point A, we do perpendicular on AP. So okay, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular. We define the touching point of the perpendicular from point O and AP. This point is point L. By doing this construction, we can do it for the other OLPM. For the other OLPM, we have 1, 2, 3 degrees. The sum of 3 degrees is 270 degrees, so 270 degrees plus the size of this 4 degrees, in total must be equal to 180 degrees according to the rule that states that the sum of degrees from any quadrilateral is equal to 360 degrees. And therefore this 4 degrees must be equal to 90 degrees in its size. In the next step, so quadrilateral LOMP consists of 4 right angles, and therefore, according to rule 5, any quadrilateral that has 4 right angles must mean this rectangle plus the square. So we relate to quadrilateral LOMP is a rectangle because it has 4 right angles. So, write it down. This is Madonna LOMP, this is the rectangle, also according to rule pi. In the next step, we will do another construction. That is to say, from point B, we will do parallel on the radius OM. Again, from point B, we will do parallel on the radius OM. So, okay, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We define the touching point of the parallel from point B and the radius OM. This point is point S. By doing this construction, you can do quadrangle SBQM. In quadrangle SBQM, we have 1, 2, 3 vertices. And therefore, this fourth missing area must be equal to 90 degrees in its sides. According to the rule that the sum of the areas in a quadrangle is equal to 360 degrees. So in quadrangle SBQM we have 4 areas, and therefore we can write quadrangle SBQM as a rectangle. So as you know, we know that the opposite sides of a rectangle are parallel to each other. And again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LPMO, side LP is parallel to the opposite side OM. Again, LP is parallel to the opposite side OM. But LP is part of the straight line AP. Again, LP is part of the straight line AP and is parallel to OM. So if a part of the straight line is parallel to another straight line, then the straight line itself AP must be also parallel to OM. So I should know that AP is parallel to OM. AP is parallel to OM. So I copy AP with the parallel line segment OM, the parallel radius OM, in a new page, and we'll implement rule 50 on those two parallel lines, and we have the third line that is the radius of the circle. So here, those are the two parallel lines AP and OM that are going from the original line. AOB is the radius of the circle. So we have here those two angles are defined as corresponding angles and they are located between the parallel lines AP and OM and therefore they are equal to each other and their sizes according to Rule 50. So quickly on Rule 50, corresponding angles between parallel lines are equal to each other. So in the drawing we have line A that is parallel to line B and line C cuts the two parallel lines at those 2 points. Those 2 angles are defined as corresponding angles and they are located between the parallel lines A and B. Therefore, they are equal to each other in their sizes. That is to say, alpha equals to beta. So we can implement Rule 50 in our drawing. Because in our drawing, we have those 2 corresponding angles that are located between the parallel lines AP and OM. Therefore, they are equal to each other in their sizes. This is to say, angle OAP is equal to this angle MOB according to Rule 50. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to Rule 50. So if you know that angle OAP equals to beta and angle BOM equals to beta also. This is angle OAP, this equals to beta, the big angle, beta. This is the big angle beta. And this is angle BOM, this is also equals to beta, degrees in size. So, in the right triangle ALO, this angle equals to beta, this angle equals to 90 degrees, and therefore this quadrant angle must be equal to 90 degrees minus beta, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in this right triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this quadrant angle must be equal to 90 degrees minus beta, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the right triangle ALO congruent to this right triangle OSB according to angle side angle rule. So according to those 2 right triangles in an equation, we prove that they are congruent to each other. AO equals to R and OB also equals to R. actually, those are the two materials that they go from the original drawing, so why those two materials can go to each other. First of all, this is again, those two angles are both equal to beta and therefore they are equal to each other. So write it down. So angle LAO LAO is equal to angle SOB in the right triangle OSB, they are both equal to beta and therefore they are equal to each other. In addition, side AO equals to side AO in the right triangle ALO is equal to side OB in the right triangle OSB, above the other of the circle and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta and therefore they are equal to each other. So they are equal to each other. So I write it down. This is angle AOL is equal to this angle OBS. They are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if I found out that those two angles and the side that is included between those two angles, that is R, of course would be equal to, in the right triangle AO, of course would be equal to those two angles and the side that is included between those two angles, that is also R, in the right triangle OSB. And therefore those two right triangles can work to each other according to angle, side, angle, wall. So if you found out that the right triangle ANO congruent, this is the sign of congruent to the right triangle OSB according to angle, side, angle, wall. Here, those two angles and the side that is included between those two angles in the right triangle ALO corresponding equal to those two angles and the side that is included between those two angles in the right triangle OSB. And therefore those two right triangles can go to each other according to angle, side, angle, wall. And from the fact that those two right triangles can go to each other, we derive that LO equals to SB. LO equals to SB according to the rule that corresponding angles at corresponding sides and congruent triangles are equal to each other. Those two triangles can go to each other, and therefore the two corresponding sides LO and SB must be also equal to each other. So if we define SB as x, that LO must be also equal to x because they are equal to each other. So if we know that LO is equal to SB, so we define LO as x, then SB must be also equal to x because they are equal to each other. So in the big rectangle LO MP, side LO is equal to the opposite side PM according to the rule that the opposite sides of the rectangle are equal to each other. But LO is x, therefore PO must be also equal to x units in its name. Likewise in the small rectangle SBQM, side SB must be equal to the opposite side MA. But SB is X, therefore the opposite side MA must be also equal to X in this line. We already found out that we found out that PM equals to X and MQ also equals to X. We already found out that MQ times PM equals to 36. So as long as we found out that MQ MQ times PM equals to 36. But MQ is X, therefore instead of MQ by X times PM. PM also is also X, so instead of PM by X. So in total, we actually found out that X times X equals to 36, so X squared equals to 36. Here we'll take out all those equations and finally found out that X equals to the square root of 36, that is 6. So X equals to 6 units in its length. PM equals to X and X equals to 6. So PM also equals to 6, of course. Here MQ equals to X and X equals to 6. So MQ also equals to 6. In the next step, we implement the Pythagoras on this right side BQM. So copy this right here BQM in the equation. We implement on it the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the source of the perpendiculars. So actually, this is right triangle BQM, the Dragovich from Dovin. This right triangle BQM, BM squared, this is the square of the hypotenuse, equals to BQ squared plus OM squared. So write it down. Let's found out that BM squared, this is the square of the hypotenuse, equals to BQ squared plus MQ squared. BM is the missing side, so electricity, so it is BM square equals to BQ square. BQ is 4, therefore BQ square is 4 squared, that is 16. Plus MQ square. MQ square is 6, therefore MQ square is 6 squared, that is 36. So now introduction formula will be M square equals to 36 plus 16 is 52. So BM square equals to 52. Here we take out all those equations and finding that BM equals to the square root of 52 units in its length. BM equals to the square root of 50 units in its length. The square root of 52 units in its length. The next step, we implement the Balanos one on this right side APM, so for me the right side APM in the equation, we implement only the Balanos one. Okay. This is right side APM, that is going from the original drawing. This right side APM, AM squared is the square of the hypotenuse, equals to AP square plus PM square. AM is the missing side, so electricities, so it is AM square equals to AP square. AP is 9, therefore AP square is 9 squared, that is 81. Plus PM square. PM is 6, therefore PM square is 6 squared, that is 36. So in total, we should find out that AM square equals to 81 plus 36, that is 117. So AM square equals to 117. Here we take out all those equations and find again that the missing side AM is equal to the square root of 117. So AM equals to the square root of 117 and MB equals to the square root of 52. Our task is to find out the Lagrange shape. Actually, the Lagrange shape is side A and B, so we have to find out the area of the Lagrange triangle A and B. So the area of the Lagrange shape, that is the area of triangle A and B, will be equal to the base of the triangle, that is MB, times the height MA over 2. Again, there are this entire AB equals to the base MB times the height AM over 2. Again, there are the entire AB is equal to the base MB times the height AM over 2. Now know that MB equals to the square root of 52 times AM. AM equals to the square root of 117 divided by 2. So if I know that there are the green item A and B is equals to the square root of 52 times the square root of 117. We have the algebraic identity that says that square root of A times square root of B is equal to the square root of A times B. According to this algebraic identity, we get that square root of 52 times square root of 117 equals to the square root of 52 times 117 divided by 2. So we have the square root of 52 times 117, that is 6084 divided by 2. The square root of 684 is 78 divided by 2. 78 over 2 is 39. So total show that there are this A and B, they are the green shape. Is equal to 39 squares in size. So we finished with the second question. In the next step of some of the lecture, I'll start with the first question, of course. The first question or test is to find out there are this pentagon ABCD. So what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interangles. This is pentagon ABCDE. It has 5 sides, 1, 2, 3, 4, 5, and 5 interangles, 1, 2, 3, 4, 5. So in the drawing we have pentagon ABCDE. We know that ED equals to 1, BC also equals to 1, and AE also equals to 1, BC equals to x, and BA equals to 1 minus x. This is a right angle. Angle EAB equals to 90 degrees in its size, and this is angle EDC, is also equal to 90 degrees in its size. Again, our task is to find out there are this pentagon ABCDE. So first of all, we join points A and B together by side line, and we join points A and C together by side line. In the next step, we extended side AB by side line in such a way that the extended part AMA will be equal to x units in itself according to our construction. So AM equals to x. In the next step, we join points A and M together by sub line. By joining points A and M, we can have the right triangle AEAM. The next step, we prove that those two right triangles can join to each other according to side angle side rule. So those are the two right triangles that are calling from the original drawing. Why those two right triangles can join to each other. So first of all, those two sides are both equal to x and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to 1 and therefore they are equal to each other. So if you found out that those two right triangles can join to each other according to side angle side rule. That is to say, those two sides and the angle that is included between those two sides in the right triangle EAM correspond equal to those two sides and the angle that is included between those two sides in this right triangle EOC. And therefore, those two triangles can join to each other according to side angle side rule. And from the fact that they can join to each other, we derive that they are also the same areas. That is to say, the area of this green right triangle EDC is equal to the area of this triangle AME. So if you define the area of this right triangle EDA as Z, then the area of this right triangle AME must be also equal to Z degrees in its size. And from the fact that those two right triangles can join to each other, we derive that EM equals to EC. EM equals to EC according to the rule that corresponding that can join triangles corresponding sides in congruent triangles are equal to each other. Those two triangles can join to each other, and the two corresponding sides, that is to say EM and EC, must be also equal to each other in the left. So EM equals to EC. Again, EM equals to EC. In the next step, a corbit triangle MEB in this triangle BAC. In the equation, we prove that those two triangles can join to each other according to side rule. Those are the two triangles that are going from the original drawing. So why those two triangles can join to each other? First of all, those two sides are both equal to 1 and therefore they are equal to each other. In addition, those two sides are also equal to each other according to what we already found out that. And if side EB is a common side that belongs to both triangles. So we write down that EB equals to itself is a common side that belongs to both triangles. So if we found out that all the triangles on this triangle E and B are corresponding equal to all the triangles in this triangle BEC, and therefore those two triangles and those two triangles can join to each other according to angle similarity rule. And from the fact that those two triangles can join to each other, we derive that they are also the same areas. This is to say, we derive that the area of triangle MEB is equal to the area of triangle BEC. So what is the area of this triangle MEB? The area of this triangle MEB is equal to the base MB times the height AE over 2. Okay, again, from the fact that the two triangles can go into each other, we derive that they have also the same area. That is to say, the area of triangle MEB is equal to the area of triangle BC. But what is the area of triangle MEB is equal to the base MB times the height AE over 2. MB is 1, AE is also 1, divided by 2. 1 times 1 is 1, so total we found out that the area of this triangle MEB is equal to 1 over 2 squared in size, or 1 half. This triangle MEB equals to 1 half squared in size. But we already found out that the area of triangle MEB is equal to the area of triangle BEC, and therefore the area of triangle BC must be also equal to 1 half squared in size. Okay, again, the area of triangle BEC also equals to 1 half squared in size. So the area of this triangle MEB plus the area of this triangle EBC total equals to 1 half plus 1 half, this is 1. Again, the area of triangle MEB plus the area of triangle BEC total is equal to 1 half plus 1 half, this is 1. Okay, but the big quadrilateral EMBC consists of those two triangles, and therefore the area of the big quadrilateral EMBC will be equal to the sum of the areas of the two triangles that it consists of. That is to say, 1 half plus 1 half is 1. Again, so the area of the big quadrilateral EMBC must be also equal to 1, because quadrilateral EMBC consists of those two triangles. Therefore, the area of quadrilateral EMBC must be equal to the sum of the areas of the shapes that it consists of. 1 half plus 1 half is 1. So the area of quadrilateral MEBC equals to 1 squared in size. But the area of this quadrilateral MEBC, this big quadrilateral MEBC consists of two shapes also. It consists of the great right triangle MEA plus this quadrilateral ECBA. So the area of quadrilateral MEBC, this is 1, must be equal to the area of the right triangle EMA plus the area of this quadrilateral ABCE. So the area of the right triangle EAM plus the area of quadrilateral EABC equals to 1, because of the fact that quadrilateral MEBC consists of those two shapes. Okay. So the area of EAM plus the area of quadrilateral BEC equals to 1. But we already found out that the area of triangle EMA is Z. So consider the area of triangle EAM by Z. So totally we get that Z plus the area of quadrilateral EABC equals to 1. Our task is to find out the area of this pentagon ABCDE. What is the area of this big pentagon ABCDE? The area of pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. Pentagon ABCD consists of this right triangle ADC. It also consists of this quadrilateral EABC, and therefore the area of the big pentagon ABCD must be equal to the area of the great right triangle ADC plus the area of quadrilateral EABC. The area of the big pentagon ABCD is equal to the area of the great right triangle EDA plus the area of quadrilateral EBC. but we already found out that the area of the right triangle EDA equals to Z according to our definition. So in total, the area of the big pentagon ABCD must be equal to Z plus the area of quadrilateral EABC. But we already found out that Z plus the area of quadrilateral EABC equals to 1. So we can write that Z plus the area of quadrilateral EBC equals to 1. And from this equation, we know that the area that we're looking for in this question, that is the area of quadrilateral ABCD equals to 1 square in size. So we finish with the first question. In the next step, we do the second question and solve the second question of this lecture. The second question, our task is to find out the area of this green shape. The green shape is showing triangle A and B, so we have to find out the area of triangle A and B. In the drawing, we have a circle. Inside the circle, we have triangle A and B. And also we know that AP equals to 9, BQ equals to 4, AB is the diameter of the circle. Again, our task is to find out the area of this triangle A and B. So first of all, we define the center of this circle. This point is point O. Here we can implement rule 7. According to rule 7, if the peripheral subset on the diameter of the circle, then it is equal to 90 degrees in size. This is peripheral angle A and B, the subset on AB, that is the diameter of the circle. According to what is given in the question, therefore peripheral angle A and B must be equal to 90 degrees in size according to rule 7. In the next step, we define this angle as alpha. So in the right hand APM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees from alpha. According to the rule that the sum of the angles in the triangle is equal to 180 degrees. So we know that PQ is a straight line according to what is given in the question. So if we focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PQ at point M? We have this angle is 90 degrees from alpha, plus 90 degrees, plus the missing angle, the total must be equal to 180 degrees according to rule 3. So I repeat again, at the upper side of the straight line PQ at point M, the sum of the angles must be equal to 180 degrees. So 90 degrees plus 90 degrees on alpha plus 90 degrees plus the angle BMQ total must be equal to 180 degrees according to rule 3. So 90 degrees plus 90 degrees is 180 degrees. So 180 degrees on alpha plus the missing angle BMQ total must be equal to 180 degrees. So here we have 180 degrees on both sides of the equation, so 180 degrees will get cancelled. And finally we get that mass alpha plus the missing angle BMQ is equals to 0. Here we get alpha this equation, and finally found out that the missing angle BMQ equals to alpha degrees in size. This is the missing angle BMQ is equals to alpha degrees in size. So in the right small triangle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees. Now alpha according to the rule, the sum of the angles in a triangle is equal to 180 degrees. It's very easy to see that those two right triangles are similar to each other according to angle similarity. That is to say, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, those two angles are both equal to alpha and therefore they are equal to each other. Finally, those two angles are both equal to 90 degrees also alpha and therefore they are equal to each other. So if we found out that all the figures of this big right triangle APM corresponding equal to all the figures of this small right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similarity. So if we found out that the big triangle A and P is similar, this is the sign of similar to the small right triangle BMQ according to angle similarity. And for the fact that those two lines are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle AMP or side AP of the small right triangle BMQ is equal to side BM of the big right triangle AMP or side BQ of the small right triangle BMQ. So AP is the missing side of electricities over QM. AP actually equals to 9, so substitute AP by 9 over MQ. MQ is the missing side of electricities, and it is equals to PM. PM is the missing side of electricities over BQ. BQ is 4. So in total, if you follow that 9 over MQ equals to PM over 4. Here, of course, multiply this equation, if I follow that 9 times 4 is 36, so 36 equals to MQ plus PM. Again, MQ times PM. So MQ times PM equals to 36. In the next step, we define the center of this, again, this point also. OA equals to R, OB also equals to R, is the radius of the circle. And we join points O and M together with a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle, this equals to R. The radius of M is equals to R is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever you know this is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MQ. If PQ is perpendicular to MQ, it means this circle, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say, from point B, we draw perpendicular on OM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OM. This point is point S. When doing this construction, we can do the perpendicular SBQM. Perpendicular SBQM, we have 1, 2, 3 vertices. And therefore this form is also equal to 90 degrees according to the rule. The sum of the rest in the quadrilateral is equal to 360 degrees. So quadrilateral SMQB has 4 vertices, and therefore it is a rectangle. Likewise, we did another construction, that is to say, from point O, that is the center of the circle, we draw perpendicular on AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP. This angle is define the touching point of the perpendicular from point A, from point O and AP. This point is point L. When doing this construction, we can do it quadrilateral NOMP. Quadrilateral NOMP, we have 1, 2, 3 vertices, and therefore this surface must be equal to 90 degrees inside. Therefore, quadrilateral NOMP, that is 4 vertices, it is a rectangle. So in the next step, we know that the opposite sides of a rectangle are parallel to each other. So rectangle LPMO, LP is parallel to OM. But LP is part of the straight line AP is parallel to OM. If a part of a straight line is parallel to another straight line, then the straight line AP itself must be also parallel to OM. So AP is parallel to OM. So in the next step, I commit those two parallel lines AP and OM in your page with this radius AOB. Here, AP is parallel to OM and AOB is the radius. Those two corresponding angles, those two angles are defined as corresponding angles, and they are located between the parallel lines AP and OM, and therefore they are equal to each other according to rule 50. So if you define the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. So okay, angle AOP equals to beta. Actually it is angle PAO equals to beta, and angle MOB also equals to beta. This is angle MOB equals to beta according to rule 50. In the next step, I commit those two right angles in an equation, we prove that those two right angles can point to each other according to angle, side angle rule. So here, those are the two right angles that are going toward the original line. So when those two right angles can go into each other. First of all, those two angles are both equal to beta and therefore they are equal to each other. In addition, those two sides are both equal, above the area of the circle and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees cos beta and therefore they are equal to each other. So if we prove that those two triangles can go into each other according to angle, side angle rule. We have those two angles and the side that is included between those two angles. These are in the right triangle A and O corresponding equal to those two angles, and the side that is included between those two angles that is also R in this right triangle OSB. Therefore those two right triangles can go into each other according to angle similar to. And from the fact that those two right triangles can go into each other, we know that LO equals to SB. LO equals to SB. So if we define LO as X, then SB must be also equal to X because they are equal to each other. This is side LO equals to side SB. So if we define LO as X, then SB must be also equal to X. Now after LO and P, the opposite sides are equal to each other. That is to say, LO is equal to the opposite side PM, but LO is X, therefore PM must be also equal to X. Likewise, in this after SBQM, side SB must be equal to the opposite side MQ, but SB is X, therefore the opposite side MQ must be also equal to X units in its length. We already found out that MQ times PM equals to 36. Again, we already found out that MQ times PM equals to 36. MQ is X and PM is also X. So X times X is 36. X times X is X squared, that is 36. Here we took out of this equation and found out that X equals to the square root of 36, that is 6. PM is equals to X equals to 6, and MQ that's equals to X also equals to 6. In the next step, I copied the small right triangle BMQ in an equation, implemented but also in this small right triangle BMQ. This is the small right triangle BMQ that is going from the original domain. This right triangle BMQ, BM square equals, this is the square of the opponent, equals to BQ square plus MQ square. BM is the missing side, so it is, and it is equals to BQ square. BQ is 4, therefore EQ square is 4 square, that is 16, plus MQ square. MQ is 6, therefore MQ square is 6 square, that is 36. So in total, BM square equals to 16 plus 36, that is 52. So BM square equals to 52. We took out all the equation, and we know that BM equals to the square root of 52 units in its length. In the next step, I copied the big right triangle APM in an equation implemented on this big right triangle APM, the pattern story. This is the big right triangle APM that I'm going to know what doing. This right triangle APM, AM squared is the square of the product equals to AP square plus PM square. So AM is the missing side, so leave it as it is. So it is AM square equals to AP square. AP is 9, therefore AP square is 9 squared, that is 81, plus PM square. PM is 6, therefore PM square is 36. So in total, we found out that AM square equals to 81 plus 36, that is 117. So AM square equals to 117. So we took out all those equations and found out that AM equals to 117 squares in size. This is the AM equals to the square root of 117, and this is side MB, that is equals to the square root of 52 units in its length. Our test is to find out the area of the side AMP, the right triangle AMP. The area of the right triangle AMP must be equal to the base MB times the height MA over 2. And again, the area of the right triangle AMB in total must be equal to the base MB times the height MA over 2. MB is square root of 52. AB square root of 52 times AM. AM is square root of 117. AM is square root of 117. So in total, there are on the letter AB equals to the square root of 52 times the square root of 117 over 2. We have the algebraic identity that says that the square root of A times the square root of B equals to the square root of A times B. According to this algebraic identity, we get that the square root of 52 times the square root of 117 equals to the square root of 52 times 117 divided by 2. 52 times 117 is 6084 divided by 2. And the square root of 684 is 78 divided by 2. 78 over 2 is 39. So if you found out that the area that we are looking for in this question, that is the area of this ring shape, is equal to 39 square units in its size. Okay, thank you very much.